Have you heard of the human cannonball? It's this old circus act in which a human being is launched from a specially designed cannon and is caught far away with a net or a body of water. Now the question of where do we place this net is dealt with by classical mechanics, and that's where we step in. Now let's say you are a hero and you want to take this daring act. Then what's the first question you want the answer for? Where must the safety net be placed? And there is no question of trial and error here, right? You won't accept it if I come and tell you, hey, let's keep it here. You jump once, let's see what happens. That's not something you're going to accept. Now also, you will want to know how high the ceiling must be if you're doing it indoors, right? Otherwise, you'll go hit the ceiling and then it doesn't matter where you place the net. So you want to know that as well. And if you're a pessimist, and if you decide that these are the last few moments of your life, you will want to know how many such moments exist. In other words, how long will you be there, flying, waiting for yourself to land on the net? Now, how do we answer these questions? What's in our control? The angle at which you can throw and the speed at which you can throw, u and theta. Now, these questions take only a few minutes to answer. Once you understand this, it will take you less than a minute to derive the answers to all these questions. And we'll prove that to you at the end of this video. Let's solve the pessimist question first, which is, how long do you have to stay in the air, the time? Now, I was thinking about what would be the easiest way to explain this or visualize this, right? Because I know we have to visualize it as two separate components. But how do we do this? Why are we so stuck up with this side view of a projectile? What other way can we look at the same thing? What would happen if instead of this view, we were to fly up and look at the same ball being thrown from the top? What would that look like? It would look like something is moving in a straight line, right? Just one-dimensional motion and at a constant speed of the horizontal component, which in this case is going to be u cos theta. Interesting. Now, is there another way we can look at it? What if we go to the front view? In other words, the view in which it looks like the person's throwing right at you, and then what's the same thing happening? Again, it's going to look like the body is moving in just one line. It's going up and coming down, right? Except that the speed at which it starts will be u sine theta, the vertical component. Now, to answer the question, how long will you be in the air? Which of these 2 points of view do you think is more useful? If you were to look at this motion from the front view, you will notice that it's as good as a ball being thrown up and coming back down again. And that is familiar, isn't it? So let's bring that over here. If you were to notice, if I had thrown a ball up at you, how long will it take to reach its highest point? U by g, right? If you're curious why, every second the velocity reduces by g. So for it to become 0, it takes u by g seconds. It's easy to do. Then for it to come back again, it will be 2u by g. So if I had thrown a ball up, it takes 2u by g seconds to go up and come down. Now what's this whole projectile motion viewed from this point of view? It's just a ball thrown up at u sine theta. So you have 2u by g, you just have to replace u with u sine theta and you get the answer for how long this person will stay in the air. A change in point of view can make our problem really simple, can't it? Now think about this again. For the question of how high the ceiling must be, which point of view do you think is useful? Again, the front view, right? Because that's the view in which you see something going up and coming down. So again, in our 1D motion, we knew this, right? If you throw a ball up at you, how high will it go? U square by 2g. It'll take you exactly 5 seconds to derive it using v square minus u square equals 2as. You can do it if you want to. So you have u square by 2g. That's if the ball's thrown up at you. But what's the ball thrown up over here? U sine theta. So you just replace again u with u sine theta. You get u sine theta the whole square by 2g. If you want to write it in another way, you can write u square sine square theta by 2g. Which brings us to the last and probably the most important question, right? Where should you keep the net? Now for this question, which view is important? Yeah? You will understand that both views are important. But if you take the top view now, so if you tilt it, and if you're able to see the motion, uniform motion along a line, all you're trying to find out is how far on this line should you place the net, right? You know the speed at which the motion's happening. So what's the only variable you need? Time. The pessimist question was answered in the beginning a little cleverly so that we can use it here. So what do you have here? Some distance that you must keep the net at. You need that distance. You have the velocity. You have the time. This is an 8th standard question, okay? Find the distance given the velocity and the time because it's uniform motion. So what's your velocity? U cos theta. What's your time? You already have it, right? U sine theta by g. Twice of that, so 2u sine theta by g for it to go up and come down. So you have the time, you have the velocity. Your answer is going to be just the product of this. Now we can rearrange this, okay, to make it look different. And you'll notice why we're doing that in the next video. So we'll do that over here. What are you getting over here? Yeah, u cos theta multiplied by 2u sin theta by g. Yeah. So 2 times u cos theta and u sin theta is sin 2 theta. Are you asking me why? Okay, fine. If you're asking me why, I'll tell you this. There is a small identity in trigonometry which says sin of a plus b equals sin a cos b plus cos a sin b. Over here you put a and b as theta, you'll get sin of theta plus theta equals, which is sin 2 theta equals sin theta cos theta plus cos theta sin theta, which is 2 sin theta cos theta. Now some of you might also ask, why is sin a plus b equal to sin a cos b plus cos a sin b? We'll not go into the derivation here because I don't know the derivation. Also because it might be a little irrelevant, isn't it? So in the final form, the question of where to place the net looks like this. U square sin 2 theta by g. Now these 3 answers have very serious names, okay? The first question, how long will you be in the air, is called the time of flight of a projectile. And how high will it go is called the maximum height that a projectile reaches. And how far you should place the net is called the range of a projectile. Now don't remember these results. Why? Because remembering or recollecting these formulae takes longer than deriving them. You want to see how? Let's say you want the time of flight. You know a ball thrown up at u takes u by g to go, v by g to come down, so overall to u by g. Therefore, you'll replace u with u sin theta, 2u sin theta by g. You're done, right? You want the maximum height. You throw a ball at u, you know it goes to a height of u square by 2g. So you just replace u with u sin theta over here, u square sin square theta by 2g. You're done. You want the range. You know the velocity is u cos theta initially. You want the time. Time is already over here. So u cos theta into 2u sin theta by g. You can rearrange it. You'll get u square sin 2 theta by g, and you're done. That's all it takes to derive all these problems, doesn't it? And that's not even the only reason to not remember these. There is a more important reason, and that is that these formulae for the range, time of flight and all that are for a special case, right? We are throwing and catching at the same height. So when you call this the range of a projectile, you're not mentioning for the special case of a projectile that was thrown and caught at the same height. And in most good exams, you will not have a problem which expects you to just plug in a well-known formula and get the answer. There'll be some change, and remembering this formula, we'll show you, might actually constrain the way in which you think. Instead of taking a simple approach, you might actually end up taking a more complex approach because you remember these formulae. Even if you do want to internalize these results, the best way to do that might be to solve problems, and whenever you need these results, just derive them. And eventually you'll reach a point where you don't have to derive them at all.
I tried what you said, but it didn't work with calculus.
Oh yeah. Except for those special cases where the derivations are really, really long, okay? Calculus might be a good example. There remembering might help.